I'm John Wu from the Advanced Technology and Testbeds Group. It's my pleasure to introduce Arpit Gupta from UC Santa Barbara to talk about making self-driving network work. So a little bit of a context here. He's recently appointed faculty scientist of ESNet, and his expertise is bringing AI and networking together. And there is one special feature in his work that maybe is not very common in academic researchers. That is, he's really interested in bringing his research results into production use. And from the more research aspect, he is bringing AI to networking, and not just, like many people you have heard, is just trying some neural network on some aspect of network. He is actually building a systematic set of tools, and he has been focusing on validating the results from his application of machine learning to networking. Okay, so I think that's the most important thing I want to mention here. He is going to join us at the all-staff retreat in August. So you will get to hear more from him about our efforts of introducing AI into ESNet operations. So sometime if you hear AI ops, that's the type of thing we are talking about. Arpit, are you ready to go?
Sure. All right.
The floor is yours.
Thank you. Thank you, John, for the kind introduction. So today I'm going to share pieces of the journey that we have been trying to get self-driving network a reality. So let's start with the basics. When we think about network or making the network, we have to think about who the stakeholders are. Obviously, the users are one set of stakeholders, but then the service provider are the one who are responsible for making the network. And when we think about service providers, there are different types of service providers out there, like cloud content providers, internet mobile service providers, community networks, last mile networks. But I think what we have been focusing on or should be focusing on is research and education network, which includes ESNet, UCSP, and a bunch of other campus networks. And all of these networks operate with different set of goals and objectives and different set of constraints. The scale and the nature of the objectives might be a bit different. But if you look at a very, very fundamental level, what everybody is trying to do is to offer secure and performant network connectivity with limited infrastructure and operational resources, right? And this is very important. And with this goal, if you look around the progress that we have made in past 1 decade, we have made some incredible progress with the concept introduced more than a decade ago, which is software-defined networking. The idea is that you have programmable data planes, which offer you a lot more flexibility. And that programmability enables you to extract more insights from the network using different type of telemetry systems and understand what the state of the network is, and then use those insights to draw some inferences about, okay, what exactly is going on, what is going on right now, what can happen in future, and based on that, make some control actions or control decisions and react to those situations, right? So overall, this closed loop that you're looking at has been referred to as network automation. And network automation is something that has been enabled with the advent of software-defined networking, right? And it's great. And I was able to, as a PhD student in my past life, I was able to make some contributions in this space as well. In control domain, I was focused more on bringing in software-defined networking ideas into inter-domain routing, starting with the Internet Exchange Point. So SDX was the work that I was working on, and that's how I got in touch with Inder as well. More than a decade ago now. And later on, I focused on telemetry systems, specifically focusing on how we can use these programmable data planes to build more effective telemetry systems. And that's like the whole line of work is under this term called Sonata. So I think overall, I would say if we have to give ourselves some credit, we should, because as a community, we made some tremendous progress starting from the early days of software-defined networking to where we are right now, where we have incredible opportunities and incredible capabilities in terms of enabling different type of network automation. But still, when we think about the network automation that is available now, powered by software-defined networking, it is still human-centric, right? So we can extract all these insights, we can take all these precise control actions, but the control loop is enabled by these predefined set of rules that we have to comprehend ahead of time. So we have to comprehend all possible situations in terms of if this happens, this is what we want to do. If that happens, then this is what we want to do, right? So this is where we are, and it works fine for majority of cases, right? So for most of the problems that we have in our network, majority of them, I would say 80%, 90%, 95% of problems, they can be resolved with these predefined set of rules, right? Now the challenge is that they fail to handle complex problems in the network, right? Those complex problems are probably the tail part of your set of problems, and majority of problems are not really that complex, but those are also very critical problems, right? So something like advanced persistent threats, which can infiltrate your network and then do lateral movements within your network, being able to detect and neutralize them is very, very hard with what we have right now, right? And in that regard, let me put into light the National Security Commission on AI report that came out in 2021. I would say it's a very critical report. I would highly recommend reading that. But there were a few takeaways for me. So one big takeaway was that when we think about AI, we think about AI is going to bring all these goods around us, like better GPT, better natural language interfaces, and so on and so forth. But it's a dual use technology. If it can help good purposes, it can also support malicious attempts and malicious intents as well. And AI-enabled tools will be the first resort in a new era of conflict that we're looking at, right? But something that really, really stood out for me was this argument that our attempts to counter AI-enabled or AI-capable adversaries with just human intelligence alone is an invitation for disaster. So this is a wake-up call for the community in general that your adversaries are not humans now. Your adversaries are these AI-powered bots. And if we are relying on our human intelligence to fight them, it's not going to be a successful strategy in the long run, right? So what do we really need? We really need to think about how we can complement or replace these predefined set of rules with machine learning solutions, right? And eventually realize an intelligence or artificial intelligence in the form of self-driving network that will enable us to operate these secure or provide this secure and performant connectivity with minimal human intervention, right? And I want to separate machine learning and AI here. So machine learning will enable AI, right? And these are two separate things. So when we are talking about self-driving network, we're talking about artificial intelligence, but the building block for that is machine learning artifacts out there. And this idea of self-driving network has been out there for, I would say, more than a decade, but it got a lot more momentum 5-6 years ago when we organized workshops targeting the self-driving network, reasoning about what the future of self-driving network should look like, what are the requirements from data perspective, what are the requirements from use case perspective. So there were a lot of discussions going on, but I would not credit ourselves saying like, oh, we were the first thinking about this idea. I would say in some other manifestation, the idea of self-driving network has been a moonshot goal for the community for a very long time. How do we realize it? What capabilities we have over time that shapes our thought process over time, right? But still, when we think about self-driving network, what we really need to think about is that machine learning models are going to be the key building blocks. And when we think about machine learning models, we really have to think about how are we going to ones that are ready for production deployment, right? So what is a machine learning model ready for production deployment? A machine learning model ready for production deployment should be the one that is generalizable, which is it generalizes as expected or operates as expected in target settings of interest. It is robust. It is not failing to different type of scenarios out there, practical scenarios out there, and it should be trustworthy. We should be able to establish trust in its decision making, right? So if that is the goal, I think as a community, we should feel some comfort because we have invested a lot of time developing machine learning models for networking, right? So machine learning for networking is not a new thing at all. It is almost as old as networking because whenever we make some decisions in networking, there is this intrinsic decision problem that has to be solved. So people have always attempted to solve those problems using machine learning tools. And there are more than thousands of papers that have been published on this topic. There are multiple startups, millions of dollars have been invested in this topic. Now, given all this investment that we have as a community, what is our expectation? Our expectation is that now, if you give me any problem, and environment where it needs to be deployed, I should be able to easily develop the model that you want, right? It should be working, it should be generalizable, it should be robust, and I should be able to trust that, right? And also, now that we have invested so much time and energy, there should be abundance of production-ready machine learning models which are ready for high-stake decision making, right? Now, what I'm going to say next is probably what you have anticipated already, which is that reality is far from this expectation. Where are we now? We are in a situation where we cannot solve all kinds of problems. The type of problems that we can solve are heavily dictated or heavily reliant on availability of public data sets, right? So these public data sets are dictating our choice of what problem we can work on and what type of environment these solutions are good for. And we do have abundance of machine learning artifacts, but we only know that they work great in controlled lab settings. We have no idea whether they work reasonably well in production settings or not, right? Now, this is the situation in contrast to what are we being asked now. So everybody in this excitement around generative AI and chat GPT excitement, everybody is now asking, looking back to us, is like, okay, where is my AI, right? Where is my AI from the perspective of networking? And as I said, like AI is a more advanced goal. The basic goal is machine learning. And where we are right now is that forget about AI, for us to get a single machine learning model deployed in production is a struggle. It's really, really hard for us to provide or develop a machine learning solution that we can convince a network operator to deploy in production settings, right? So now you might be wondering that, like we are all smart people, worked so hard for 10 plus years on this topic. Why are we here? Why are we not building AI that everybody's asking us yet, right? And I think the answer is that the problems that need to be addressed for us to solve or develop these generalizable machine learning models is fundamentally very challenging. And we didn't really make good choices when we embarked on this journey. For example, when we think about developing a machine learning model, the first thing that might come to your mind is this standard machine learning pipeline, where you are providing some data, it goes through some pre-processing, model selection, training, evaluation, then you have a model, you have some performance scores. Based on that, you make some decisions about whether it's ready for deployment or not. Now, the problem with this machine learning pipeline is that it has been adopted as is from other application domains, right? Computer vision, NLP, and other domains, right? And what it expects is that the user should know what is the right data, as if it was such an easy thing for us to do, especially in context of networking. So now, because this responsibility has been shifted to the user, then user, like to the best of the judgment, use some data. And if, depending on how hard or easy it is to get that data, they put some data in. And if you end up inputting garbage into this pipeline, then only garbage can come out of it, right? So if I really care about developing models that generalize, I really have to answer this question, which is that what is the right data, right? Now, let's assume that somehow I'm able to figure out what is the right data. The next problem is, how am I going to collect this data, right? When it comes to data collection for networking or data in general for networking, the nature of network data is such that it necessitates endogenous data collection. Now, you might be wondering, why am I saying that? So let's take a step back. When we think about machine learning models, most of the solutions that we have right now, or we have been exploring so far, are supervised learning based solutions, right? So those need labels or ground truths. Now, where are you going to get the labeled data from, right? So one approach is that I can go back to my production network and collect some data from my production network. That's great. It's very realistic data. But then associating that with some ground truth is very hard, right? So you don't really have an abundance of, for all types of problems, you don't really have labeled data set available. So what people end up doing is to do endogenous data generation, data collection, which is like endogenously generate new data under different type of emulated environments, such that they have the ground truth information as well, and the data and the training data that is used for training or for developing the model, right? So now if I have to think about data collection as an additional step for this pipeline, then I also need to answer, how do I collect the right data? If somebody tells me this is the right data, then I also need to answer, how am I going to collect that right data, right? Now, when we think about data collection, we also have to realize that data collection is fundamentally hard, right? So it's not that nobody has collected any data in the past. There have been some efforts, but most of these efforts are very fragmented in nature. What do I mean by that? That most of these efforts focus on one or two type of problem and one or two type of network environment. For me, to leverage these past efforts to create or generate data for a new problem or a new environment is extremely hard. So this over specialized effort makes data collection very hard. And what we end up doing is that since it is such a high threshold activity, nobody wants to invest time collecting data. So people are happy working with data that already exists. And that is why we are over relying on these publicly available data sets. A bad thing about it is that it restricts the type of problems and environments we can focus on. And I'll talk about more bad things with the public data set as we move forward, right? But that's where we are. That's a challenge because data collection is so hard. So we are restricted with what data we have right now. But even let's assume that even if you have collected the data that you are looking for, and you were able to train a machine learning model, and the model that is offering you a good performance is a black box model, so you don't really understand how the model is making its decision, and you don't know whether this model is going to generalize or not. The standard machine learning pipeline is offering you no assistance in trying to figure out whether this model is going to generalize or not, right? So I don't know if this model is underspecified. When I say underspecified, the model might be learning a shortcut, model might be overfitted to the training data, or model might be learning spurious correlation, which is coincidental but non-causal relationships in the data, right? So if I don't know any of this, I don't know whether I've trained something which is ready for production deployment or not. And I know that this might sound a bit overwhelming, a piece of information. So let me take a simple example and help you understand what I'm talking about in terms of challenges when I really care about developing a model that is ready for production, right? So suppose my goal is to develop a machine learning model that is able to identify onset of these HTTP brute force attacks, right? This is something which is very common first line of attack that the malicious actors will try and get into your target HTTP servers. So if I'm a researcher, I would look around and okay, yes, CICIDS is one data source. There is this cybersecurity or cyber security institute somewhere in Canada that is curating this data set. So first question is this the right data for the problem of the environment where I'm going to go for? But in most cases, I really don't have choices. So this is the data set that is available. I'm going to use it. Now I have used this data set, trained a machine learning model, and the pipeline is showing me that its F1 score is 0.99. So in principle, I should be very happy and say okay, this is such a great model. It's giving me such a good high performance, but I do not know whether this model is underspecified or not, right? I don't know if this model is learning something which is very specific to this training data, which might not be generalizable to other target settings where I really want to deploy this model, right? And even if I somehow know that, say, for example, this model was learning a shortcut to make its decision, and it was not really learning anything meaningful from the data, I don't know what else I can do to collect something which is better than what already exists, right? So for me to reason about how am I going to develop models that are going to generalize, I really need to answer these fundamental questions, which are extremely, extremely hard, right? And that brings to the present of where we are in our quest for building self-driving networks, right? So for past few years, I've been working on this idea called closed loop machine learning pipeline. So let's see what is closed loop machine learning pipeline. What we argue is that there are all these flaws with the standard machine learning pipeline, so we should be augmenting it. And even if we are very, very smart researchers, we don't always have the full sense of what is the right data for a problem. So let's not put the onus on the user to say you have to figure out what is the right data. Let's say to the best of our intuition, we start with some data, right? And we should be simplifying how we collect this data endogenously from different type of production environments. But let's say we are able to do that. We are able to collect some data, and then we train a model. But rather than reasoning about the model suitability for deployment based on just the F1 score of performance in general, let's try to explain and analyze model's decision making. How is this model making its decision? Is that model vulnerable to some type of underspecification issue? And create some type of analysis report and send that to a domain expert. Let domain expert take a look at it and identify or infer whether this model is making the decisions as it is expected, or it is vulnerable to some obvious underspecification issues. And if it identifies some problems in the model and it is able to map those problems to the data set, then this expert should be able to go back and refine the intents of collecting the data, collect different data. And the idea is that if you do this iteratively enough, then you might be able to improve the quality of data that you're using for developing the machine learning model. And that would help you improve the generalizability of the model itself. Now, we have been putting effort realizing this pipeline. So as I said, you need to collect some data. So for that, we have built Pineo, which is basically a set of tools which simplify how you can transform your production network into a data collection infrastructure. Then we have Trusty. So Trusty is a model explainability framework that explains and analyzes models decision making. And we have NetUnicorn, which simplifies how you can iteratively collect data for any problem from any target environment, right? Now, I know this might be overwhelming and I'm throwing out a lot of information. So let me break this down a bit more. So when we talk about Trusty, Trusty is a post hoc, which is like you train the model and then it is applied after that. And it's a global. So it tries to, rather than explaining how model is making decision for an individual data point, it tries to understand how it is making holistically, how it is making decisions for all the data points. And it's an explainability framework. What it essentially does is that it takes in the training data set that you have used for training the black box model. It takes in the black box model itself and then give you explanations of model's decision making in terms of a decision tree. And the tool is model agnostic. It is high fidelity. It demonstrates low complexity as well. And it is offering you stable explanations. But in the interest of time, I'm not going to give you details of how we built it and how we demonstrated everything. I would rather focus on what it enables. So what Trusty enables can be explained with this same example that I was discussing before, which is like, if I want to develop a model for detecting HTTP brute force attacks, I have the CIC-IDS dataset. I use a multi-layer perceptron. And if I apply that to the standard machine learning pipeline, it's giving me 0.99 score, right? So in theory, I should just go out to network operators and say like, look, I developed a machine learning model with great F1 performance. You should just deploy this, right? But when I use Trusty and try to understand how this model is making its decision, I understand that, oh, the majority of decisions are made based on just the TTL value. And now you might wonder why TTL value. And it kind of like all boils down to how this data was collected. And this is something which has been used by 100+ papers out there, right? So what really happens in this infrastructure is that the malicious hosts are in one subnet, the benign host is in another subnet. Each of them have different number of hops to reach to the target server. And that's why each of them have different TTL values. And the model, obviously, it sees this easy way to make classification between benign and malicious hosts, and it picks that, right? So because the data had these skew, so the model learned a shortcut, and this model is underspecified, that is, it cannot generalize. So if you make some changes to the input, it's not going to make the right decision. It's just going to fail miserably, right? So this is an instance of shortcut. Now let me show you when we applied this to a broad range of like solutions out there, and which were trained using different set of public data sets out there. What each of these solutions were reporting was that they were achieving very high F1 score, and based on that, like they were the state-of-the-art solution out there, right? But the question is, can we, based on that, can we just trust them for production deployment? And when we applied Trusty, it told us no, don't do that. So we identified different instances of underspecification issues that were affecting these state-of-the-art machine learning model. Our focus was, of course, more on network security here. So some of them were learning a shortcut. Some of them were having out-of-distribution issues, but that is, they were not generalizing for out-of-distribution samples. And then there was spurious correlation issue, which is that like the models were learning something which was coincidental but non-causal relation in the data, and it was making good decisions based on that. And overall, I think what this tells us is that because of all these underspecification issues, these models are not going to generalize. So if you try to apply them in target setting of your own network, they're going to fail miserably, and this is what we showed in the paper as well. But what is more important here is that we also showed that most of these problems are actually attributable to the public dataset. And remember, I was saying there are two problems with the dataset. So one problem is that it restricts what type of problems, learning problems, you can attempt to solve. And second, most of these data sets are curated in a way that either the network that they're trying to emulate is not realistic, or like there are some other problems with how the data has been collected or processed. And overall, these data sets are skewed enough that they do not provide enough opportunities for us to even try develop something which is likely to generalize, right? So this data set is a problem. Now, what do we do, right? So if we cannot just use public data set, we really have to think about ways in which we can create or curate data set of our own, right? And the idea is that we should be able to use the insights that we are getting from a solution like Trusty, which is telling us how model is making a decision, what are the problems with the data set, which is contributing to this underspecification issue. And if we are able to map these things, then we should be able to refine what data needs to be collected and collect that new data, right? But if you're paying attention, you might sense the contradiction in what I'm saying here. I'm saying that collecting data is so hard, and public data set is what people have, converged on. And that is problematic. To solve that, I'm saying, like, let's collect new data and collect it more iteratively, collect more and more data, right? But because data collection is hard, given all these fragmentation that exists out there, that all the previous efforts collecting data are specifically or over specialized for one or two problems or one or two type of environments. And I cannot, if I come up with an idea that this is a new problem for which I want to collect the data, or this is a new environment from which I want to collect the data, there is no easy means for me to amortize previous effort and start collecting that data, right? So we identified this as a problem. And what we built was something called NetUnicorn. What NetUnicorn is trying to do is to realize this thin waist, where at the top you have different type of learning problems. At the bottom, you have different type of environments which are emulated over different type of physical or virtual infrastructures out there, right? Now, essentially what it means is that it is simplifying how you're going to collect data or express or realize your intents for collecting data for different type of learning problems and from different type of network environments, right? So in interest of time, I'm not going to get into the details of how we realize that goal. I will encourage you to take a look at the paper that we published at CCS last year. But it provides us, it's an interesting case study into how we are going to build the system, what type of abstractions are needed, what type of mechanisms need to be realized. But what I'm going to focus on is what it enables, right? So in the previous discussion that we had with Trusty was able to demonstrate that there is a learning shortcut for the HTTP brute force attack problem. Now, let me show you how NetUnicorn and Trusty together can help realize the closed loop machine learning pipeline and make models more generalizable. So let's start with the first step, which is that I, as a domain expert, will collect data to the best of my intuition, right? And what we did here was that we tried to follow whatever previous communal understanding was, which is that how data collection intents were expressed for the CIC IDS case, which is the public data set out there. And we were able to mimic or emulate, or not even emulate, replicate exactly what CIC IDS did with 80 lines of code using NetUnicorn. Then we considered, 4 different type of machine learning models. And then we considered a setup that, which is a very common setup, that I have a target environment where I want to deploy, which is the cloud. And I can collect data from my own campus network, which is a local environment, right? Now, when I collect this data, I have performance of F1 score of 1.0 almost for all the problems. But then when I try that on the target data set, the performance is extremely low, right? Like close to 0.5 for most cases, right? Now, when we dig in, what we realize is that it's the same problem that we saw before, which we identified before with the original data set. It's just that we were able to reproduce the same problem here, and TTL was the bigger problem that because the TTLs were fixed for benign and malicious hosts, so that's how the model was making its decisions, right? Now, this is where the interesting part begins, which is this is what you can do with the public data set, right? CIC IDS is given, you find this problem. What do you do next is important. Now, what we do next is that we should be able to fix this problem, which is that I should be able to now maybe divide or distribute these benign and malicious hosts in a way that the distribution of TTL should be realistic or similar to what I would expect to see in production environment, right? So this is what a change that I would desire to be realized here. And we were able to do that. But what is important here is that with NetUnicorn, it just required us additional 10 lines of code. So we initial setup was 80 lines of code. Then we made 10 lines of code change here. And then we were able to get this new data set out there. Now you see that when we have the source dataset campus, the performance is still close to 1, which makes me suspicious, right? Close to 1 is always suspicious if problem is challenging enough. And then what we observe when we apply that on the target setting is that there is a big gap between what you see on the source data versus what you see on the target data, right? Now that implores that we have to investigate what's going on. So we applied Trusty, try to understand what's going on. And we observe that now the model is actually learning a new shortcut. So there is this specific feature which is indicating that the target server is overwhelmed. It is getting too many requests out there, but that can be correlated when the server is under attack. But it's not always a causal signal, right? So every time a server is busy does not mean that it is under attack, right? So this is in some sense it's an artifact of how this data was collected rather than an artifact of how you would expect things to be in real world, right? So we went back and we said, okay, this needs to be changed. So we changed again, and we tried to refine the intent and using like separate TCP connection for each attempt so that the server is not overwhelmed and this specific feature is not getting skewed in there. Again, this required only 10-20 lines of code change for us. Now, when we see the performance on the source data, like the numbers have gone slightly down. Some models are still close to, the random forest is giving you 0.97. And then we apply that on the target data set. We observe that the drop is not significant at all, right? That it's very similar to what we are observing in the source data set, which is telling me that, what we have been able to do here is that what the data set that we are curating in our local campus network is closer to what we are expecting in the target settings, right? And this whole iteration took 2 or 3 steps for us, but now we're getting closer. And we looked into the decision tree as well, and we didn't really find any obvious candidate for learning shortcuts or any other under specification issue. So it tells us that we were able to curate over these iterations, we were able to curate data set that was better than what we started with. And I want to be very careful here and say, we do not claim that we have solved this generalizability problem for good. It is only indicating that we are doing better than what we were doing before. The model is not getting distracted by all these obvious shortcuts or obvious under specification issues. There might be more subtle issues here, but this is not a formal proof or theoretical guarantee that there is no under specification issue with the model that we have trained. We are doing better, right? With this each iteration we are improving, and the data set that we have is letting model likely to generalize here, right? So this closed loop machine learning pipeline is simplifying how we develop models that are likely to generalize and that are free from under specification issue. Now let me move on to what this whole thing is building up for, right? So where we are in a situation where we have built these different set of tools, which is simplifying how we collect the data. It is letting us explain models decision making. Based on that, we're able to refine our intents, enable this iterative approach. But at the end of the day, what we are collecting is an endogenously curated labeled data set. Now, what is important to note here is that the quality of data set that I'm able to curate here will heavily rely on how well I'm able to emulate realistic target environments, right? And to be honest, doesn't matter what I do. If I want to build something for something like ESNet, it will be very hard for me to mimic everything which is closely resembling what ESNet's infrastructure is on my campus network, right? There is going to be a big gap, and there might be some issues. I might be able to avoid obvious pitfalls, but it might still not be bridging the trust gap that we need to cross over. But what is another thing here is that when we think about the infrastructure that we have built, which is enabling us to curate this labeled data set, what it also offers is the ability to collect this unlabeled telemetry data, right? So we can, configure our network and generate new data set, and this is what we are using for the closed loop machine learning pipeline. But with all the advances that we have made into telemetry systems, for us, collecting unlabeled telemetry data in abundance is relatively easy. Now, the question is is there anything that we can do that can help us tap into this potential of unlabeled data out there, or I would say abundant telemetry data, which is unlabeled out there? Can we do something? And this led to this whole thought process for us, which is what about foundation models? So foundation models have gained a lot of success and traction in other application domains. I think some of you have already heard about LLMs. So LLMs are essentially foundation model for the natural language processing domain, right? What it really means is that if you provide some unlabeled data, it does pre-training and tries to understand that spatial temporal relationship using self-supervised learning techniques that don't require any ground truth labels. And you're able to train a model that is a foundation model. And then this model can be fine-tuned for different type of use cases that you have in mind. In context of networking, what we're talking about is that if we input this unlabeled telemetry data, and it is abundant thanks to SDN-powered telemetry infrastructure, and I think it's especially relevant in case of ESNet, where you have the high-touch telemetry infrastructure in place. So unlabeled telemetry data, if we are able to apply the self-supervised learning techniques, develop this foundation model, then what we can do is that we can then fine-tune this for specific use cases that we want to solve. And what is unique about this whole process is that now the model, because we are using this foundation model, we are learning more intricate contextual relationship between different parts of the data and different contextual information out there. So it can still work, or it can, or at least we can expect it to work with reasonably well with the data for fine-tuning data, which is sparse and noisy. So, right. So as I was saying before, that doesn't matter what I do with my like data generation, it might still not be representative of the realistic network, because it will be sparse, it will be noisy, it will have some type of skews, one skew or the other, right? But the foundation model is more immune to these problems, these intrinsic problems that we have with the labeled data set out there, right? So this whole pipeline, I think it's important to understand that we are starting with unlabeled data set, applying these self-supervised learning techniques, extracting as many insights as possible, as many meaningful relationships as possible in the data, and then we are fine-tuning it to specific use case using the labeled data set. And the labeled data set that you're using for fine-tuning it's okay if it is sparse, it's okay if it is noisy, if it is okay if it is skewed to some extent, right? And it offers an incredible opportunity for us to catalyze the development of production-ready machine learning for networks, because it is liberating us from this fundamental limitation that we have right now, which is that the data is sparse, skewed, and noisy, right? So because we are doing this pre-training, that's what is liberating us. Now, the question you might be asking is that I mentioned LLMs before. The obvious thing is that LLMs already exist. So why don't I just throw it to networking problem, right? Why don't I just apply LLM to network data? Now, network data is not natural language data, right? There are fundamental differences between what network data is and what natural language is. And if we try to do this type of naive approach, we might have some success, but it's not a long-term solution, right? And I should help identify what are the fundamental differences between network data and natural language data. So when we think about network data, and I'm narrowing the scope only to packet traces, the easy thing. So when we think about packet traces, the packets, the content in the packets is embodying different type of protocols. So when I'm thinking about how do I tokenize, I really have to think about what type of protocol, like I have to be aware of what type of protocols and logic is in place, right? Then the sequence length is variable depending on what sequence I'm looking at. Am I looking at the sequence in terms of packet, in terms of group of packets as bursts, group of packets as flows, group of packets as hosts? There is this variability that exists in the sequence length. And that because I cannot just have infinite length sequences when I'm training these type of models. So I have to make some selection in terms of what tokens are worthy of taking in for training, right? And then when we think about network traffic, it itself, the packet traces itself are capturing this multimodal information. So there is interesting information within a packet, across packets within different bursts, across packets within different hosts, across different flows, and so on and so forth, right? So all this multimodal information, which is capturing this critical spatial, temporal, contextual information, needs to be captured. So we have to think about how are we going to embed all these tokens together with each other. And then the network data is intrinsically hierarchical, that there is this inherent grouping that happens within the network. As I said, you have the packets, then packets are grouped into bursts are grouped into flows into different services into hosts into networks and links, and so on and so forth. So there is this whole level of hierarchy that goes on, and we have to think about what is the right way of modeling this data, right? So I will stop here in terms of technical detail, but I'll not talk about how we solve this problem, but I will talk about the implication, right? So what we did was that we developed a domain-specific network foundation model, and we solved, I would say, less ambitious, obvious problems to demonstrate the value, right? So we chose the problems that already exist, are already well-explored problems, and tried to demonstrate that with the foundation model, we are able to solve them better. And we also showed some results demonstrating that they're more robust to the noises, they are more robust to the underspecification issues that trouble these things. But we were able to make some decent argument that it can outperform state-of-the-art solutions out there, right? But when we try to take a step back and think about where are we right now, when we talk about foundation models, where we are is that we are able to develop these performant and generalizable solutions to well-explored learning problems. And this is a good start, but we want to go forward, right? So we want to think beyond this, and we don't want to restrict ourselves to just packet traces. We want to make sure that we are having this full spectrum of telemetry data ingested into the foundation model. So not just packet traces, the IDS alerts, the logs that we have from the applications, the MIB information that we have from different devices, the syscall information that we have from different end hosts. We want all that information. And if we want to be more ambitious, we should also think about the code, right? So you have your own specialized, customized server code running on different type of application or different type of servers out there, different type of client code. I would like to take that into consideration as well and use this multimodal heterogeneous piece of information to learn different type of hidden context that would be important for me to make some good decisions or solve problems that have not been solved before, right? So I mentioned solve problems that have not been solved before, the unexplored problem. Let me give you a quick sense of what I'm talking about when I say unexplored problems, right? There are different type of unexplored problems. There are uh, foundation model is making us ambitious. It is telling us that you can attempt things that have not been attempted before. There are these less ambitious problems, I would say, which are like low hanging fruits in some sense that, oh, this LLM already exists. Some representation of network data exists. Maybe we should merge these two worlds together and think about how can we build these natural language interfaces so that we can interact with the network data and figure out what the state of the network is, and maybe also take some actions, right? So if I communicate that if this happens, take these type of actions in natural language, it should be processed into some set of queries over the telemetry data and set of configuration actions in the network, right? So this is something which I would say is very feasible right now. It is, to me, it's more of an engineering effort that needs to be put in place, but I would categorize that as a less ambitious goal, right? Let's think about something which is more ambitious than that. So something more ambitious than that is that we should be able to predict future, right? So look at all the telemetry data that I have in the past. I should be able to predict what type of traffic pattern am I going to expect, when I'm going to expect it, where I'm going to expect it, right? And I should be able to do that not only for the known application that I have in my network, but also the unknown part, right? Which should help me identify what type of malicious activities are going on in my network. And I should be able to do that, apply this type of predictive power and do to achieve that goal, right? I would say this is something which is less clear in terms of how exactly that's going to get realized, but it's moderately ambitious. If you want to do more, and I think this is something which has been discussed in the ESNet community as well, like what if, like when we talk about the workflows here, there are these scientific computing workflows that we typically worry about, right? What if we are able to enable this packet to packet, code to packet, packet to code transformations? What I mean by that is that if you're writing a program, and if you're able to tell that what line of code will translate into what packet in the network, or what packet in the network is coming from what line of code in your client or at your server, that would be fantastic, right? Because that would enable me to do this type of debugging of my program ahead of time, do all this pre-planning before, and also in real time able to figure out what, when I see something malicious, where it's coming from, which part of the code or which part of the configuration is responsible for that. And packet to packet transformation is also very important, which will help you with this post hoc analysis, that when you were sending traffic for application A, but if you were doing application B, which is in essence a counterfactual analysis, that if it was application B with algorithm B or C or D, what would it look like, right? So that's what I'm talking about when I say packet to packet translations. So this is something I would rate as extremely ambitious, but something which is feasible within the realms of things that we try to do, right? So let me try to converge all these things together. So if I want to peer into the future, I think that what is possible is that we should be able to build a trillion plus parameter network foundation model. We should be able to offer that as a service, which is basically do some global pre-training, amortize all the efforts in one place, and then this should be offered as an API access to different type of network out there, which can individually apply their own closed loop machine learning pipeline to fine tune the machine learning models and develop and solve problems of their own. And of course, it's challenging. So it will require us to explore a lot of fundamental research questions. But I would say that we are at a stage where I see that these are all feasible solutions. Yes, these fundamental challenges have to be addressed, but that these are not the deal breakers for us in terms of thinking about how foundation model can be practically deployed in production settings. And to sum it all, I think this whole thing ties up to this goal that we want to build production-ready machine learning models. The combination of closed loop pipeline plus foundation model are the ones that are going to be the key enabler of how we are going to develop machine learning models that are ready for production deployments. And that will be the enabler for the self-driving network. So I'll end this talk now. Just for reminders, so like in this talk, we were talking about past, present, and future. And in the past, we were talking about software-defined networking. What we're doing right now is closed-loop machine learning stuff. And what we want to do as we move forward is the network foundation model. And this is how these things are connected with each other. So I would end my talk here, and I will be more than happy to take your questions.
Thanks, Arpit. Questions from anyone? think maybe this is a lot of information to digest.
Arpit, I have a question. Have you done any kind of fine tuning to the available foundation models, and have you seen any interesting results?
Yes. So I think John shared the paper. So we have fine-tuned for one, we have trained a foundation model using the campus network data at UCSB, and then we have fine-tuned that for the problems that I was showing before. So and also we did fine-tune, in the process we did evaluate. So if you see the solutions here, so ETBERT and YATC. So ETBERT is basically the LLMized version of network foundation model, and YATC is basically an application of vision foundation model in context of networking. So we did try to compare and contrast with these existing solutions as well.
Thank you. By the way, great talk. Thank you so much.
Thank you.
So, Arpit, based on what you see happening, I mean, you have a much more insight into the academic marketplace. Do you see a lot of network researchers focusing on the foundation model? What do you see the landscape like? And are you hearing anything from the big commercial companies that tend to build products or jump on hype bandwagons on what their approaches to this is?
Absolutely. I think, both things are true. So yeah, this is where I was. So yes, I think, so first answer, yes, I think, a lot of people in academia are interested. I would say it's natural for them to get excited because everybody has been frustrated with this challenge or fundamental limit that we have applying machine learning models or machine learning techniques to network problems, that we don't have data to work with, right? So now if somebody is telling me that we can liberate you from all these data clutches, then I think, it's very empowering and a lot of people are working on it. I would say, as I was saying before, that people will focus more on low-hanging fruits, high-value low-hanging fruits, which is like, okay, let's think about LLMs and just apply LLMs as is on network telemetry data. And I would say there are a bunch of startups from academicians that have already popped out in this direction. But I think, over time, you really have to demonstrate value by doing something more fundamental. I think if you want to invest in long-term strategy, I think you have to think about what is the most first principled approach of solving these problems. About interest in industry, I would say, I'm already working with AWS and Cisco, so they're excited about this whole idea already. And there are a bunch of other companies that are interested. I think a lot of interest is coming in terms of how do you make better use of the telemetry data that already exists. So many companies have invested so much in building their telemetry infrastructure, and they're looking for how can we apply LLM to extract more value out of it. I think there is more holistic approach required where you have a whole network stack where you think about telemetry data being represented, having intermediate representation that can be interfaced in natural language with using LLMs. So I see both of these things have to be there in place. But you can expect to see a lot more commercial solutions coming out in the space in the next 2 to 3 years, maybe sooner.
Alex, I see your hands up.
The anomalous data records are relatively a small portion. How do you handle the class imbalance problem in training the model?
Right. So I think it's very problem specific. So I think it comes to the first part, which is when we are talking about closed loop machine learning pipeline. So because we are doing endogenous data collection, so we control how much and what type of traffic we collect and generate. So that gives us flexibility in terms of identifying class imbalance. So we don't solve it as a first order thing. But when our analysis tells us that because of the class imbalance issue that we have in the data, it is leading to underspecification issue. So then we try to fix it, but we have means of fixing it by increasing the number of samples that we generate for a specific underrepresented class.
Yeah,
Anyone else?
yeah, I would also
Yeah, go ahead.
I would also just like to say, that was a great talk. I really enjoyed it. And I saw a lot of parallels to DOE internal proposal I'm working on. So really great talk. Took a lot of notes, and it would be great if I could check in with you at some point.
Oh, absolutely. I'm on Slack now.
Anyone else? Maybe while we're waiting, I do have a question about the work of Trusty. You had an illustration, you know, after 2 iterations, you think Trusty is not giving you obvious signals of some under-specification problem. Is there a way, or are there possible ways to make that more rigorous rather than just say we look at it and it seems to be not any real problems?
Right. No, I think so. You're absolutely right. I think, like that's, I would say, one of the limitation of Trusty. Trusty has been widely successful because there were so many obvious problems with the existing machine learning artifacts and data set out there. As things get more subtle, it gets more challenging with using Trusty as is. So we're working on hybrid explanations, which is like, combining local explanations with these global explanations to zoom in on specific subset of data points to figure out how the model is making decision for this entire subset of data sets and try to iteratively zoom in terms of which part of the data is more interesting and try to identify problems there. The other techniques that we are looking for is also based on perturbations. So we are trying to there's this general theory of underspecification where if you do some perturbation on the data set and if you get equivalent classifiers or equivalent models, then that is a good indicator of underspecification issue. So we are trying to make it a bit more rigorous, combine all these techniques that exist in classic machine learning literature and apply that in context. Like, what does it mean for networking, right? Because compared to everything else, what we have is ability to generate data, right? So, or iteratively generate data, right? So when people talk about solving these problems in the machine learning sense or the computer vision area, they talk about passively augmenting the existing data set. For us, passive augmentation becomes new data generation. So that's the divergence that we have to think about. But there are a lot of existing techniques that we can leverage on in the machine learning community that can help us improve the solution.
Thanks. Anyone else have questions, comments? I think maybe not too many of us have really been thinking about this type of problems, and so or need time to digest.
Yeah, I can make these slides available. So if there is any other follow-up that needs to be done, we can do that.
That's great. Arpit, I was going to post the recording when we have it both in the area Slack channel and on the ESNet Slack channel so that everyone here could access it. But if you're willing to share slides, that's great too.
Yeah, I'll be more than happy to share.
Thanks.
Right, cool.
Well,
I also want to say that this was recorded, so I think the people, if you guys like the presentation, you can share it with your colleagues who are not in the meeting and who would benefit from hearing this. Sorry, back to you, John.
Well, I guess let's give Arpit a virtual round of applause for the great presentation, and we'll be seeing him a bit more at the all staff retreat in August, and look out for potentially more AI ops type of activities within the ESNet, right? So, and if you are interested, reach out to me or to Arpit directly, and we can talk about what we could do to do some exploration of making use of these wonderful tools for ESNet operations, right?
By the way, if I have a minute, John, I would like to say what faculty scientist means because people may not know it. Faculty scientist means that Arpit is he's a faculty at UCSB, he's doing his work, he's managing his student. But he is member of ESNet. So when we want him, we can have access to him, but it has to be managed and controlled in the sense that his time is, he still has his day job as to speak. He's not left UCSB. So I think we need to make sure, absolutely feel free to ask questions and everything. But if you want him to start working on a specific problem that you have, then we need to have that discussion.
So maybe by default, I'm the gatekeeper then.
In not so many words, that's what I was trying to say, that I don't want Arpit to become the bad guy saying, hey, I have no time. I want you to manage that, John.
Yes, I will be the gatekeeper. So reach out to me if you have interesting ideas and want to chat and explore ideas.
All
Thank
right. I think I just want to say that thanks for letting me have this talk, and thanks to all for giving your 1 hour of life. I really appreciate that. And I think I'm excited about working at ESNet and thinking of ways in which these ideas can actually be transformed into something real. That's the biggest motivation for me. And I think I'm looking forward to work with you folks. And I will be attending the retreat. So if you plan to attend and if you have questions for me, feel free to reach out. We can plan something ahead of time as well. Thank you.
Thanks
Thank
and
you.
bye, everyone.
Bye.